This is section 8.2, vectors in the coordinate plane. A vector OP in standard position on a rectangular coordinate system, as in figure 8.2.1, can be uniquely described by the coordinates of its terminal point xy. We denote OP on the coordinate plane by xy, and we're going to use the chevrons to denote that this vector is in standard position. Notice that x and y are the rectangular components of OP, which is saying we have OP and it's the rectangular components, meaning that the x coordinate is the horizontal component of this vector and y is the vertical component of the vector OP. For this reason, xy is called the component form of a vector. Since vectors with the same magnitude and direction are equivalent, many vectors can be represented by the same coordinates. For example, vector p, t, v, and w are equivalent because each can be denoted by 3, 2. In other words, the horizontal component of any one of these is 3, and the vertical component of all of these vectors is 2. So we can represent all of these vectors with the component form 3, 2. And we use what's called the chevrons to denote that we are reporting these vectors in standard position. The component form of a vector AB with initial point A as x1, y1 and terminal point B as x2, y2 is given by we subtract the x's and we subtract the y's. Think about when you're given 2 points. Let's say this point over here is the point 3, 4. And this point up here is, let's say, 10, 15. Now, if you're going to go from 3 to 10, that's 7 units. From 3 to 10 is 7. So to find this distance, you can take 10 minus 3, and that'll give you the 7. Then, if you're going to go from 4 to 15, that's 11 units. So from 4 to 15 is 11. We can take 15 minus 4, and we get 11. So this will be the horizontal component, and 11 will be the vertical component. So the vector in standard position, that would be the same as this one, is 7, 11. Example 1. Express a vector in component form. Find the component form of AB with initial point A as negative 4, 2 and terminal point B with 3, negative 5. So we write chevron, we write 3 minus negative 4, and then we write negative 5 minus 2. So we're writing x2 minus x1 and y2 minus y1. And we get 7, negative 7. Magnitude of a vector in the coordinate plane. If v is a vector with initial point x1, y1, and terminal point x2, y2, then the magnitude of v is given by, and this is just the distance formula. And the distance formula comes from the Pythagorean theorem. So how do we find the x-coordinate, or the x component? We subtract the 2 x's. And to find the y component, we subtract the y's. Find the magnitude of AB with initial point A as negative 4, 2 and terminal point B of 3, negative 5. So the magnitude of AB is the Pythagorean theorem, or the distance formula from A to B. That's equal to, let's see, we need x2 minus x1, 3 minus negative 4, and we'll add that to negative 5 minus 2. Oh, and we need to square these, of course. So we have the square root of, let's see, 7 squared plus negative 7 squared. That's equal to the square root of 49 plus 49. And that is equal to the square root of 98. Is the length of that vector, or the magnitude of the vector. And of course, we could find out what the decimal value of square root of 98 is by using our calculator. In example 3, we're going to look at operations with vectors. If the standard form or the component form of vector w is negative 4, 1, y is 2, 5, and z is negative 3, 0, we are asked to add w plus y. And that is negative 4, 1 plus 2, 5. And we just add the x parts, so that'll be negative 2, and we add the y components, which will be 6. And that's all there is to it. For z minus 2y, we take z, which is negative 3, 0. We're going to subtract 2 times y, which is 2, 5. And to multiply a vector times 2, that's kind of like the distributive property, I suppose, where you multiply both the x component and the y component times 2. So we have negative 3, 0, and that's going to be minus 4, 10. Negative 3 minus 4 is negative 7, and 0 minus 10 is negative 10. Unit vectors. A vector that has a magnitude of 1 is called a unit vector. It is sometimes useful to describe a non-zero vector v as a scalar multiple of a unit vector u with the same direction as v. To find u, divide v by its magnitude, which is denoted kind of absolute value v, but that means magnitude. So to find the unit vector, we take the vector components and we divide by the magnitude. So we're going to find a unit vector u with the same direction as this vector right here. Now this vector's magnitude is the square root of 4 plus 9. It's the square root of 13. And of course, square root of 13 is not 1. But it's the magnitude of the vector. Now we're going to take v and divide each component by the square root of 13. So the unit vector is equal to negative 2 over square root of 13 and 3 over square root of 13. Now this vector has the same direction as the original one, and the length of this one, or the magnitude, is 1. Now we can test that to see if it's actually 1. We can square root the first one squared. We have 4 over 13, and plus, if we square this one, we have 9 over 13, which is the square root of 13 over 13, which is square root of 1, which is 1. This vector has the same direction as that one, but has a magnitude of 1. This is the answer we're looking for. The unit vectors in the direction of the positive x-axis and positive y-axis are denoted by I is the unit vector along the x-axis, and j is the unit vector along the y-axis. And here are the vectors right here. If we have I, which is in component form or standard form, is 1, 0. So we go to 1, 0, and the initial point is at the origin. So here is a unit vector, a vector with length 1, and it's going along the x-axis. Likewise, we have a unit vector that's going along the y-axis, and it's denoted by the point 0, 1, where the initial point is at the origin, and we go up to 0, 1. So this vector has a length of 1, and it is going along the y-axis. These vectors can be used to express any vector v in AB as AI plus BJ, as shown in figure 8.2.4. Well, let's start out with a vector AB, and we can use an actual numbers here. So let's say AB was 3, 4. We can write this as 3 times 1, 0 plus 4 times 0, 1. And let's do the vector operation to see why that's true. 3 times 1, 0 would be 3, 0. We'd multiply 3 times 1 and 3 times 0, get 3, 0. And then we can multiply 4 times 0 and 4 times 1. And we would get actually 0, 4. Now when we add these two together, 3 plus 0 would give you 3, and 0 plus 4 would give you 4. So we end up with the exact same thing. But rather than writing 1, 0 and 0, 1, we use the letters that are associated with those two unit vectors. I is 1, 0 and j is 0, 1. So we can write this vector, this is the same as 3i plus 4j. let DE be the vector with initial point -2, 3 and terminal point 4, 5. Write DE as a linear combination of the vectors ij. Well, first we need to get DE in component form. So that's going to be 4 minus -2 and 5 minus 3, which is equal to 6, 2. And then to write that as a combination of the vectors I and j, we write that as 6i plus 2j. We want to find the component form. Find the component form of the vector v with magnitude 10 and direction angle of 120 degrees. So we have an angle of 120 degrees. That's 120. And we want to find the horizontal component and we want to find the vertical component. Now we have the length or the magnitude of the vector is 10. So we want to find the horizontal and the vertical components. Now to find y, we can do the sine of 120 is equal to y over 10. And the cosine of 120 is equal to x over 10. And now we can multiply both sides by 10 in each. So y is equal to 10 times the sine of 120, and x is equal to 10 times the cosine of 120. So when you find the component form and you're given the magnitude and the angle, you just need the magnitude of the vector times the cosine of the angle, comma, the magnitude times the sine of the angle. And that'll work for any problem where you're given the magnitude and the angle. Let's find the actual answer. We have 10 times the cosine of 120, which is a half. And we have 10 times the sine of 120 degrees, which is the square root of 3 over 2. So the component form is 5, 5 square root of 3. Example 7, direction angles of vectors. Find the direction angle of each vector to the nearest tenth of a degree. This vector here, p, which is 3i plus 7j, can be written as 3, 7. And if we put that vector in standard form, we start at the origin and we go over 3 and we go up 7. So here's the vector right here. And so the horizontal component is 3, the vertical component is 7, and we want to find that angle. We want to find the direction angle. Well, we can use the tangent of the angle that we're looking at. Let's call it theta. The tangent of theta is equal to 7/3. And so theta is equal to the inverse tangent of 7/3, which when we put this into the calculator is 66.8 degrees. Let's try the same thing with letter B. We have 4, -5, and the tangent of theta is equal to y over x, or sine over cosine. We have -5 over 4, and when we plug that into the calculator, we get inverse tangent of -5 divided by 4. We get -51.3 degrees.